and welcome back to another video about the industrial automation. Today we are going to talk about failsafe PLCs, safety controllers or FCPUs. This is a very interesting topic, at least for me, because there are too much to learn and too much to talk about. I even know people who got their PhD on this topic. So I totally understand it can be overwhelming to get started, even if you have a lot of background in the PLC and industrial automation. So the goal of this video is provide you as much information as possible to help you get started on this topic. So in the next few minutes, we are going to talk about why you need a safety PLC, what is the difference between a safety PLC and a normal PLC, and then we are going to learn more about what Siemens has to offer when it comes to safety integrated controllers. And in the end, we are going to write a program in the TIAPortal environment to implement some tasks such as programming and controlling safety door and also emergency stop or e-stop in a live demo. So be prepared and make sure you follow along and take note. And without further ado, let's get started. Okay, so the first question that you might ask is why we need a safety controller, or when do we need a safety controller? So this is a very great question. It's better to understand why we are doing something before getting into the details. So there are too many reasons, and in here I just listing what I think is an answer to this question. And the first answer is to achieve a higher reliability. So that means the standard PLCs are not fail-safe. Of course, they are very reliable. They are built or designed for industrial environment, but there's always chance to fail. No one has guaranteed that. So using a safety controller, we can guarantee that the output or the inputs are correct, because there are many strategies to make sure all those information are accurate and the data is not corrupted. The second reason is because we are using a safety controller to promptly respond to critical event such as e-stop. We don't want to mix our emergency stop signal with the normal signals in PLC, such as reading a sensor or writing an actuator, because when the e-stop is pressed, something has gone wrong and we have to immediately perform some actions to make sure everyone is safe and our process is shut down in the safe manner. The next reason is we want to have a better management on our software and hardware, especially when we are working on a complex system. In some degrees, you can achieve some performance of the safety controller using a normal PLC if you are a very good programmer using the interrupts and making sure all of these blocks are called in a certain time. But when the system becomes more complex, you cannot manage all those sequences and especially your cycle time. Using a safety controller, all these things are managed using the processor or failsafe controller or FCPU, and you don't need to be worried about anything. Another reason, of course, is we want to minimize the downtime by faster fault diagnostics. In a safety controller, you have more functionality to find the fault and the reason why that fault has happened. You cannot do the same thing using the standard controllers because you don't have access to all those features and fault diagnostic capabilities. Another reason that you need to use a safety PLC, not just a standard PLC in some application, is you want to basically track every single change either in software or hardware. Or in other words, you want your controller have the change traceability using some predefined and standardized mechanisms such as F signatures, which we will talk about shortly. And that's one of the most important reasons that you need a safety controller. Last but not least reason for using a safety controller versus a standard controller is compliance to some regulation and standards for some particular application. So it is mandatory to use a safety system to get certification for your system or your machine. and yeah, you cannot get all the certificate if you don't use this equipment. So some most common use cases for safety systems or safety controllers are handling the emergency stops or e-stops, handling some tasks such as two-hands operation, and another common use case is safety doors and also safety live curtains. You don't want someone go inside a machine. Let's say you have a fast running conveyor belt. Once someone opens the door, you want your system shut down. That's another very common use case. There are other use cases such as safety interlocks between different processes and different machines, and also safe speed monitoring of some moving device such as servo motors or induction motors and so on. So now let's see what are the main components of a safety system. Regardless of the manufacturer of the safety controller or safety system, every safety system consists of, first of all, a detection system or a sensor. This detection sensor or component can be a push button for emergency stop or restop. It can be a proximity switch or magnetic switch for detecting whether a door is open or not, and so on. The next component of the safety system is a device that evaluates the current state of the system based on some predefined logic and the information that comes from the detection system or component. This component can be a safety integrated PLC, such as S7-1200 or 1500 offered by Siemens, or other safety relays and other safety components offered by other manufacturers. And the last part of a safety system is a reaction. So once you detect an event, you evaluate it, and now you have to react based on the information that you have received and based on the logic that the programmer have implemented. The reaction, it can be like a contactor, a solid state relay, or just a command to a VFD to speed up or down or even shut down a conveyor, for example. So now let's see what Siemens has to offer when it comes to fail-safe controllers and safety system. So I put the link over here, and we can just quickly go and review all the information over there. But before visiting the website, I have to emphasize that one of the most important thing about any safety controller or safety device is having the certification. All the Siemens safety modules, the IDOs and so on, and also FCPUs are certified by TÜV for application level up to SIL or safety integrated level 3 and performance level E. So let's go to the Siemens website and understand what are the different options when you want to write a safety program or implement a safety controller. So there are too much information, as I mentioned, to talk about the safety controllers and safety system. But in this page, you can find a good amount of information to get it started. For example, as you see in the middle of the page, Siemens offers these type of controllers and safety system. The first thing and most basic one is S7-1200 with safety integrated. You might have already worked with S7-1200 CPUs as just a standard PLC, but there are some particular models that they are fail-safe and you can use them in a safety system, and they are certified by TÜV, as I mentioned. So the first family of CPUs is 1212FC, and this is the by the way, this is the CPU that we are going to use in today's demo. And the second family is CPU 1214FC and 1215FC in different version. And of course, apart from the base unit or the controller itself, we have access to digital inputs and output and some special outputs and inputs for S7-1200. And in today's demo, we are going to use one of the FDIs or digital inputs, and also one FDQ or output for demonstration and writing the program. The next category of controllers with safety integrated offered by Siemens is through the S7-1200 family of controllers. Of course, this is more advanced compared to S7-1200. You have access to more functionality and more features compared to S7-1200. And again, there are some particular models that support safety. And of course, S7-1500 also offers some fail-safe digital input and output and special DI and DQs, and you can just select based on your requirements. So the next category is distributed controller with safety integrated, which are 8200 SP or 8200 Pro fail-safe PLCs or CPUs. And but this is more useful for distributed applications. If you have like a central rack, you might just use a 1500 or 1200. And another option that you might consider using is an open controller by Siemens. So this ET200SP open controller is also available in a safety version, and you can basically see what options are available based on the model numbers and the operating system that you need and so on. And last two category of safety system is a software controller with safety integrated. As you may know, software controller is a piece of software that you install on an IPC or industrial PC, and there is a safety version of that as well. And as you can see here, then those models are called 1507 SF and also CPU 1508 SF. And the last part is the drive system, SIMATIC drive controller with safety integrated. So these are basically designed more specifically for using in a motion system, controlling the speed of motors and so on. And overall, yeah, these are the main categories offered by Siemens when you need a safety system or safety integrated controller. Now let's see what are the main differences between the normal CPUs and FCPUs. One of the main differences is a concept called coded processing. All FCPUs use a principle called coded processing, which in this process, the safety program is processed twice by a single processor. So in other words, when you write a safety program, when you compile the program, the CPU or the TIAPortal creates another system function blocks, another set of system function blocks, which does the same thing as your user program does, and then in the end it compares the results of all this program to make sure the data is not corrupted. So after understanding the main differences between the FCPU and the normal CPU, let's see what are the main differences between the inputs and output in the safety system or safety integrated controller. Let's see one example. As I mentioned, e-stop or emergency stop is one of the common use case for a safety system. As you can see here, when you use a safety or FDI or digital input card, you will have a pair of inputs to be wired to emergency stop button, for example. As you can see here, you supply the voltage on one side and you read the voltage on the other side in one of the channels, and let's call it channel 0. And on the other side, in the second input in the pair, you supply a voltage and you read the feedback or the signal on the channel number 4 or the other input in that pair. Okay, I know it was too much of theory, and without further ado, let's get our hands on a live demo and program a safety PLC, and I will walk you through about to the hardware and also the software, and we will test the program after we finish our program in the TIAPortal. This is a demo case that we are going to work on, and we will configure it and we will write a program, and ultimately we will test the system. As you can see here, this is a simulation for, let's say, a cutting machine. Let's say we have a machine and the machine has a door, and when the users or the operator open the door, we don't want the system to be running we want to immediately shut down the system. Here we have a CPU 1212 FC, and this is a DC version. As you see here, the CPU already comes with some digital inputs, 8 inputs, and also 6 outputs. But keep in mind, even the failsafe CPU, the DI and DOs on the CPU itself are not failsafe. So the CPU, you can just use it for processing a failsafe program, but you cannot use the inputs as a failsafe. That's why on the right side, we put a signal module 1226, which is failsafe digital input, or FDI, and also we use the SM1226, which is a FDQ, or failsafe digital output. If I'm not mistaken, this is a 4 digital output card, and this one is a 16 digital input card. And as I mentioned, our system consists of a door, and that's why we have this piece over here. This is simulating the door. As you see here, I can just open it or close it, and this is a sensor, proximity sensor, magnetic sensor, to detect whether the door is open or not. And we have a light over here which simulates the running motor. This could be a command to a VFD or in any motor, but apparently here on a demo case we just want to have a light, and that means right now the light is on, and that means the motor is running. And on the lower right, we have the emergency stop button, and also we have a reset button to acknowledge any fault and alarm. And on the left side, we have 2 relay contactors by Siemens, and these are 24 volts. So in other words, we wired the inputs, or inputs in the systems are the sensor, emergency stop, the reset button to the PLC, and also the output from the safety car output card are connected to the relay contactor. And these are just the wiring, as you see here. Okay, so 2 things that I need to mention. The first thing, the emergency stop, as you may already know, has 2 outputs, or 2 contact, as you see here. Those are 2 normally closed contact that we wired them to the FDI 0 and 8. So these are the pair channels 0 and 8, and I will show you in the program. And also, as you can see over here, apart from sending the command to contactors, we are reading the 2 feedbacks to make sure the contactors are on or off, and we just connected them to just a normal DIs of the CPU. Before getting to this TIAPortal software, I just want to show you how the system works, and then we'll get into the details how you can write the program. And so again, as you already saw, the motor is running right now, the power is on and the motor is running. Once I open the door of the machine, the system automatically shuts down. The program that we wrote is so that there is no requirement for acknowledgement just for the door. So that means once I close the door, the system goes back to normal in a running state. But if you press the emergency stop, as you see here, there is a acknowledgement request by the CPU. And that's why you have to press the reset to send the acknowledgement and put the system in a normal condition. Without further ado, let's jump into the TIAPortal and see how we can program a system like this. Okay, so we are in TIAPortal, the software for programming and configuring the Siemens PLCs and other devices. This is the same software that you're going to need for programming the safety controllers or PLCs. The safety component or option is not included in the TIAPortal by default, and you need to install it as a separate option, and you need a separate license for that. That's something you need to be aware of. So once you install the safety component to your TIAPortal and you add your safety PLC, you will have an option or a subcategory called safety administration. So this is the heart of your safety controller or safety system, where you configure your safety functionalities and you can get some information and so on. So let's just get started from the beginning, which is configuring the hardware, what you need to configure and what different parameters mean and so on, and then we can get into the logic and introduce you all the functions that you can use. As you saw in the demo application that we have here, we have one S7-1200 CPU, and also we have a FDI, which is 1226, and a FDQ, another signal module 1226, but this is the digital output module. And let's see what are the required configuration that you must do to use this the safety feature. Okay, on the CPU side, you don't need to do much settings related to safety. And something to know, if a property has something related to safety, you will have this yellow flag next to it. So for example, in the CPU, as you see here, we have this failsafe new option. If you don't have a failsafe CPU, you don't have this option. And the first thing, you have to either enable or disable your safety feature. Please keep in mind, as I mentioned, if you don't have the safety option in your TIAPortal, this option won't be available for you. But you can still program your CPU similar to just a standard CPU, but honestly that doesn't make sense, because failsafe CPUs have more features and functionality, and when you purchase a safety CPU, you want to use the safety capability of that. And another property that has been added to the safety controller compared to a standard controller in the safety is the safety access level. And as you see here, we have the yellow flag. So you will have this new option, which is a full access, the highest level of access for safety PLCs. That's really it for the CPU part. Like a normal CPU, you have to configure your IP address. And in my case, my IP address is 192.168.02.01. And also I have enabled the web server, because I'm going to show you in a second that we have a custom web page that you can see some custom content related to the demo panel. Unlike the CPU that we didn't need to do much setting or set some parameters for related to the safety, but in the safety signal modules, you have to do quite a bit of settings and set some parameters, especially for digital inputs. As you see here on my digital input card, I have F parameters, and also I have access to my digital inputs or DI parameters and channel related. As I mentioned, the safety inputs are paired. That's why you see the name of two channels next to each other. We have channel 0 and 8, 1 and 9, 2 and 10, 3 and 11, and so on. So let's see what are the most important parameters to change, and honestly most of the parameters can be left as default, because TIAPortal takes care of all of those for you and selects the right one, but based on your specific application you might need to change some of these parameters. Okay, on the F parameters I'm just going to leave everything as default, but something to know, all this for example this F destination addresses, this is for profit safe related, which is a unique address that you need to watch out in your network to make sure these are unique. And also the reintegration after channel fault, this is one of the important things to consider. We will talk about, so what does that mean is so the way safety modules work, if something goes wrong due to, let's say, communication error or bus fault or data corruption, it will passivate the module or that input and output. So what this parameter means is if you want to reintegrate that passivated module automatically, or you want to have control over it, maybe let's say press a button to do that and so on. In our demo, as you saw, we have a reset button, so we are going to use that one to reintegrate the modules to the system. Okay, on the DI parameters, and one of the most important parameters that you need to know are in the channel related, especially for digital inputs. So the first parameter is sensor evaluation, and that's something that I already mentioned. So in a digital input, we are dealing with a pair of inputs. So here we are saying how the evaluation should be. So I'm just saying here 1 out of 2 evaluation. I have another option that which is 1 out of 1 evaluation, but in let's say for example in the emergency stop, because we have 2 inputs, output from sensor or push button and 2 inputs to the PLC, I'm going to use 1 out of 2 evaluation. And in the type sensor interconnection, I'm going to say 2 channels equivalent. What does that mean? It means my 2 inputs from the e-stop button should be the same all the time. There are some sensors that will give you opposite signals. For example, one input is 1 and the other 0 and vice versa. But in the e-stops normally, and the e-stops that I'm using, they are both normally close contacts and they always give the same type of signal. That's why I'm going to use 2 channel equivalent. And the next parameter is discrepancy behavior. So here it says, what if I found out the inputs are not the same? Because you define 2 channels should be the same, but what if they are not the same? So here I'm just going to say supply the value to 0, so that just instantly initiates the input to 0, but I can select to set the last valid value to make sure my process and machine is safe. And also there is another parameter called discrepancy time. That means basically this time, let's say for 50 milliseconds in this example, this discrepancy or evaluation is done. Once they are different in more than 50 milliseconds, it will throw an error or fault that there is something wrong here. I just define that the sensor based on your type sensor interconnection, the inputs are not bad, so something must be wrong. And of course you can just activate or deactivate the channels, but I just suggest to activate what you have basically wired up. If you haven't wired up an input, just disable them to avoid any accidental noises or just overall accidental behavior of your program due to the noise. And another parameter that you need to know is channel failure acknowledgement. As I mentioned, you have 2 options, either automatic or manual. In our demo, as you saw, when I opened the safety door, I didn't need to send the acknowledge signal, and that's why for my safety door I will select the automatic, but for my emergency stop I put the manual. That means I have to enter or define and acknowledge a signal for that. And also the sensor supply, you have 2 options. Either you supply the sensor internally or externally. In my case, as I showed you on the drawing or on the sketch, I supply the emergency stop with a signal from the card and I read from the other side. So that's why I put the internal. Those are all the parameters for digital inputs that you need to activate. And the good news is for digital outputs, really you don't have that much parameters. But on the digital output, same, you have the F destination address. You can just again define the reintegration after channel faults and DQ parameters. Similarly, so the most important thing is activate it, activate the channel if you use it, and also define the channel failure acknowledgement, whether it should be manual or automatic. So that's pretty much it for the configuration of the cards and the hardware. So now we can go into the software and see how we can write the program, what to configure, and so on. As I mentioned, the safety administration window is the heart of the safety system in this safety integrated controller by Siemens. So once your hardware is configured, all the parameters are set, you just come over here And this is there are just a lot of terminologies if you are not familiar with the safety system. But the first thing you have is the F runtime group. You need to define at least one runtime group. As you see here, you just define a name, and then you just define the safety function block name, and you define the priority and cycle time, number of OB, and so on. So the way the safety program is running is through the organization block. So basically, this function block, or FB1, main safety RTG1, will be executed in the OB123 here every 100 milliseconds. That's how this function is executed, and you can write your program and logic in it. And I'm going to show you in a second how all of those are done. Again, there are other parameters if you want to go further in details, but as a basic, this is just a basic parameter that you can define. For example, you can pre and post processing of the F runtime group. You can define, okay, before running this function block, do this, and after you called it, do that, and so on. So if you go to our program, so for sure, as I mentioned, this is the FOB or function block runtime group 1, and which is being called in the OB1 of 1 to 3. We define this OB number over here, and if we go to FB1, that's a function block that we called it here. We have our logic implemented in this function block. The programming of safety is done through the predefined and certified function blocks for you, and these are all TÜV certified, provided and tested, verified, validated by Siemens. And as you see here, you have different function blocks for different tasks, and the most common one are emergency stop, and you have two hands operation, you have feedback and safety door, acknowledge, global acknowledge, and so on. So in our example, we have one EM emergency stop. That's why we use one ES stop 1 block. This block is very simple, as you see. So all you need to do is you just define where is your safety input or emergency stop button is connected. In our case, we connected to I8.0, but I just used my symbolic tag that I defined in the hardware configuration that I just showed you. And then I'm going to say either the acknowledgement is necessary or not. In the emergency stop, we always recommend to use the acknowledgement recommended, because if someone pressed the stop, we want to know what was the reason. We want to go there manually, hit the acknowledge before putting the system into the normal condition. So if I put this parameter to false, once my ES stop button is released, the system will go back to normal condition. And here, well, because I defined it as to be true, I need to define an input to act as an acknowledgement signal. And in our example, as I show you, we have a push button to acknowledge that. And on the other side, on the output, so basically this is the ES stop OK signal, let's call it. You can use it in your program. And apart from the Q and or the output, there's another signal called acknowledgement request, and basically once the ES stop is pressed and released, and because this is true, we get the acknowledge request, and this is connected to the light on the ES stop that I showed you. That's how we know that okay, an acknowledgement is required, and then we press the button. The next function that we are going to use is the safety door. As I showed you, we have that door that once we open, we want the system to shut down, but we don't want to have the acknowledgement. That's why we put it as false. Once the door is closed, the system goes back to normal. So for the safety door, we have two inputs that shows the door is closed or open. In this case, we connected those to connect normally closed signals to I87 and 9.7, which are channel 1 and channel 2. And similar to ES stop, we'll get an output using in the other section of the program, and then the acknowledge request again. And in case if you have the acknowledge necessary here, You can use this as an to interlock to acknowledge the signal. So on network 3, because my system is not that complicated here, I could have several thousand, not thousand, couple hundreds of e-stops and safety doors based on the scale of my system. But here I only have one of each. And in the third network, I have used another block called feedback, which I'm going to use to make sure everything is okay on the system, and then I'll generate a safety interlock OK signal. So in other words, first I'll check if the door is closed and e-stop is okay. These are the outputs from these two blocks, and that's how this block is on. And then on the feedback side, as I showed you, I got two feedbacks from the contactors to make sure they have operated, because they are normally closed contacts, and I'm going to read back and make sure they are okay. And then that's the feedback signal. These other inputs, QBAT, FIO, these are module specific signals that you can use in your program. If something goes wrong, you just get a high or 1 in this bit value, so you can use it in this block as well. And this block also, of course, you want to have a acknowledge necessary, and then you just use the same bit in our example I7.0.7 to acknowledge the signal. So the output of this signal block is signal which called safety interlock OK. That means everything is fine in my system related to safety. So now I'm going to use that to start the motor. This is the FBD or function block diagram, and I'm just going to connect that directly to a motor running. Once everything is fine, I want to run my motor. Everything is not fine, or one thing is not right, I turn off the motor. And then I use another function called acknowledge global. This is for reintegrating the faulty modules. If everything is, one of the modules is faulty, you need to, as I say, based on the setting that we've done, we need to acknowledge it, and that's the signal that you need to reintegrate those. You can do it manually as well, but it's just easier to do a global. I'm just setting the contactors for sure to turn on and off the motors once the safety interlocks are okay. So that's pretty much it about my safety program, and I have a e-stop and safety door up and running. And let's go to other section of the program, and then I can go online and I'm going to show you how things will work in the real time. So in this demo, apart from the safety program, I have a custom web page. If I enter the IP address of my controller, I get the landing page. Maybe I'll just move myself over here. Okay. So this is the web server of the controller. This is available for almost all the PLCs, not just safety, but as you see here, you can just get some information. I forgot to mention this. So in the safety PLCs or CPUs, you have something called a signature. What does that mean? That's basically, as the name says, it's a signature. Every safety program has a unique signature. If you change something either in the software or hardware or even the communication part of the network, this signature after compilation will be changed. So you can track if someone has changed the program, and also you can recover the program with a known signature. So also you have access to all these diagnostics, and of course diagnostic buffer of your CPU. These are the last entries in the diagnostic buffer. You can also access to TIAPortal, as you know. You can get information about your module information. As you see, I have FDIs, FDQ, and they are all okay. As you see, they are green. Communication and so on. I'm not going to every single detail. That's like a separate video, not just safety related. And another thing I wanted to show you, that's the important one. So as I mentioned, I have a user-defined web page. So this is a user-defined web page. Okay, maybe let me just move myself somewhere in this corner. Okay, so this is a very simple graphical representation of my demo. As I mentioned, I have a main CPU, one DI, one DO, the safety door, contactors, emergency stop, and so on. So I have two dynamic objects over here which shows the motor status, either running or stopped, e-stop okay or e-stop pressed, and so on. For example, maybe I can just trigger the door right now. The e-stop. Okay, watch out here, the motor will go stop and the e-stop will be e-stop pressed, right? So once I release it, the status will go back to normal. So that's the user-defined web page. This is not just for the safety, all the safe PLCs from Siemens 1200, 1500 support this. As I mentioned, my program, apart from this safety part, has another blocks or just a general of normal functions to update that web page. That's why I have some program and FBs inside this OP1. That's how I update those blocks. So again, that's the beauty of using a safety integrated controller, because you can use the information of the safety system in the normal PLC and vice versa. So as you see here, I just use my e-stop status to kind of move it to a parameter that I'm using to update this parameter and show different pictures based on different tag, the value in the tag. Okay, so let's just go and go online and let's see the safety door. As you see here, I have two inputs. They are both true, and the safety door close is true. There is no acknowledgement request. So once I open the door, as you see here, my inputs are false and output is false, and then it trips the motor and the motor is not running anymore. And because there is no requirement for acknowledgement, once I close it, it will go back to normal. But on the other hand, for the e-stop, as you see here, my e-stop status is true and the output is true. Once I press it, it goes to false, and also my feedback goes to false. That means that my interlock is not valid. And because I set the acknowledge to be necessary to be true, once I release the e-stop, my output is still false, and it waits for me to press the acknowledge, which I'm doing now, and it goes back to normal. Okay, that's it. I hope you enjoyed this video. Please make sure you leave a comment and let me know what you think about this video, and feel free to connect with me on LinkedIn and also chat with me on the comment section below and here. Until the next video, have a great day.